Hi everybody, I'd like to welcome you everybody to the CITA Circular Economy Series 2021, presented in association with GMIT, the Irish Green Building Council and the CIOB. My name is Mark Kehily and I'm based in the Department of Building and Civil Engineering in GMIT. And I'm delighted to step in for Alan to host this event today. Okay, sure. That'll be played again anyways on their website. Sorry about that. So what I do is I'll introduce today's session. So today's session is focusing on introducing life cycle and whole life carbon thinking. We have a number of excellent speakers this morning. First up will be Stephen Barrett, the whole life carbon project lead with the Irish Green Building Council, followed by David Stockdale, director with Briga Consultancy Limited, followed by Mirko Furnitani, the Embodied Carbon and Circular Economy lead with Hilson, Moran, and finally Dr. Dermot Kehily is a lecturer in TU Dublin. Just before we start, could I ask all attendees to turn off their videos and mics if they're not already off while the webinar is underway, and post any questions in the chat facility as we'll have a Q&A at the end. So to kick off, I'm delighted to introduce Stephen Barrett from the Irish Green Building Council. Over to you, Stephen.
Thank you. Hi, everybody. I'll just share my screen and we'll get going. Let's see, there we go. So I hope you can all see this Join Building Life slide. I'm going to take that as a yes. So IGBC is part of the World Green Building Council initiative to drive awareness around our building materials and why it's important that we understand more about them. Decarbonising buildings is not only about not burning fossil fuels to heat our homes, it's also about how we build in the first place. And the Building Life campaign is here to highlight the embodied carbon in the materials that we use in such huge quantities. Now, we all know that, that buildings are pretty impactful. They account for about half of everything we currently mine out of the ground, about a third of all our emissions, and about a third of all of the EU's waste. When we talk about whole life carbon, we're referring to the carbon emissions in the building materials, as well as those caused by energy use in the building during its useful phase. And it's these materials that I really want to highlight today. So this is quite interesting. New regulations are appearing all the time. This is a World Bank slide that demonstrates if you take this slider at the top of the page and slide it back to 1990, you'll see that only Poland and Finland had any kind of carbon pricing regimes in place. And you slide that forward to today, and you can see the speed at which this is proliferating around the world. The French government is probably leading the way in building in carbon into its procurement procedures. So in the future, if you want to win infrastructure and building contracts in France, this is going to be crucial. In France today, you can't make any environmental claims about your products unless you have the data in the form of EPDs to back it up. Holland now requires whole life carbon assessments for planning permission. It's been written into the new London plan, and this is starting to proliferate as other cities follow suit. Finland is aiming for net carbon neutrality by 2035. There was a Chinese announcement at the end of last year announcing their net zero trajectory for 2060, and the US has just rejoined the Paris Agreement. So you can see how this is only going to become more important. This is the same data. It just shows the proportion of the world's carbon emissions that are currently subject to some form of pricing regime. So you can see we're currently taxing in some way around 23% of all emissions, and it's only going up. So The aims of the Building Life campaign is to reduce embodied carbon by 40% this decade and work towards zero embodied carbon in all our new buildings by the middle of the century. Currently, the EPBD only looks at the energy use of our buildings, the operational energy, but of course, a building doesn't just appear. Its whole life cycle is much more. And although the operational energy is usually the greatest emitter in a building's life cycle, as we build better, more efficient buildings, this operational energy becomes less important and the other aspects of the building become just as important. So I modeled a typical concrete block house, and this is what a new A2 rated home would look like today. I'm going to show you a few charts, but they're all based on this same data, just displayed in different ways. Today, an electric heated home with an A2 rating, which is 50 kilowatt hours per square meter per year, would have a carbon cost of around 9 kilos of CO2 per year. This factors in everything: electricity generation and transmission, the fossil fuels that are still used in the grid. Now, the National Planning Framework has a target of 500,000 new homes by 2040, and these all need to perform at this A2 rating. So as the grid decarbonizes and becomes more efficient, we would expect the 9 kilos in this operational energy portion to reduce. So this is the same data. That operational energy is the top half. You can see that's all electricity use, but it's the bottom half that I want to focus on, the carbon emissions associated with the building materials themselves. There are other factors, but that's what I'm going to be looking at today. So again, this is the same data, only showed over time. You can see at the bottom there, the 50 years of the model. That yellow line at the bottom is the carbon emissions spread over the 50 years useful phase in the building's life cycle. But it's the big burp at year zero that is the elephant in the room. That's made up of manufacturing materials, what we call the A1 to A3, transporting them to site and the actual construction of the building itself. Now, the problem is they are happening right now. They're not spread over the future and based on a decarbonizing grid. So it actually looks more like this. You can see that same 50-year life cycle at the bottom, but as carbon dioxide stays in the atmosphere, it has a cumulative effect. So while we would expect that dotted line to flatten in reality as the grid decarbonizes, we're setting ourselves a starting position of over 40 tons of CO2 from 20,000 houses every year. So you can see why that embodied carbon really does need to be addressed. So the problem, we're not really aware of our own impacts. So I'm going to try to relate them to something that we're all more familiar with. The average car sold in Ireland in 2019 produces 122 grams of CO2 for every kilometre driven. So we're going to take a look at some of our key building materials and see how they stack up with this. So here's our car, 0.122 kilos of CO2 for each kilometre. So if you compare that to a kilo of concrete, a kilo of concrete is about the same as driving your car 800 or so meters down the road. I should say that throughout this, there is variance. Just as you would get variance depending on the model of your car, there'd be variance in the concrete and all the other different materials that we're going to look at based on the energy mixes used to produce them or where the raw materials were sourced from. But everything I'm using here today is an average drawn from groups of comparable EPDs or modelled using average background data. So here we have a brick, just one brick, the same as driving your car, about almost 4 kilometres. And I'm told that we use about 70 million bricks every year. So that's about 250 million kilometres of bricks that we use every year. The mortar that holds them together, just 1 kilo. And concrete blocks, the same as driving 46 kilometres in your car. So you can see what I'm trying to do here. I'm just trying to show you the things that we take for granted and give you an idea of what it really takes to get them ready for site. So back to our car. Now this slide highlights the importance of recycled content. A kilo of structural steel beam requires more than 3 kilos of CO2 emissions to produce, but this can be reduced drastically with increased recycled content or looking into alternatives. And of course, alternatives sometimes come with extra benefits. So a kilo of timber will sequester over a kilo of carbon dioxide. It draws the carbon out of the atmosphere and uses it in its growth phase and leaves that oxygen element where it is. So aluminium for facades and windows, it's great for weatherproofing and it's light, it's infinitely recyclable, but the production method requires huge amounts of electricity, even when some of the content is recycled. It also comes with some other pretty nasty side products too. There are great pools of this useless red sludge dotted around the world as a result of our aluminium production, but they're out of sight, so they're out of mind. Last one, our insulation. So wood fibre has about the same carbon cost as EPS, but it also absorbs carbon as it grows prior to harvesting. So this cubic metre could balance out around 860 kilometres of driving emissions, even after you take into account the emissions that it cost us in producing that cubic metre. So, so this sequestration is important and we need to hold on to it as long as possible. We need to think about how we can reuse it after this building has served its purpose, after it's deconstructed. Because if it's incinerated, then the sequestration is lost and we're back to square one. I think Mirko's going to talk a bit more about buildings as material banks and the circular economy. So I'm just going to leave that there for the moment. Now, everything I've shown you has been simplified, and there could be 100 other reasons for choosing or not choosing a specific product. But I just wanted to clearly show the difference in one property, the carbon cost. All the materials, other properties would also influence the decision making. This final bar chart shows an external wall build-up using CLT and the same external wall using cavity, using concrete blocks. This one's in percentages, so the worst performer is 100% on each chart. And you can see in the first chart, the GWP, global warming potential, this is the carbon, that can be reduced by 70% by switching to CLT, but there are other environmental impacts. The CLT performs worse on the ozone depletion potential, for example, in this case. The carbon indicator is usually a good indicator for the other impacts, but it's not certain. So we have to tread carefully. And you can see on the right there that the CLT obviously does have that sequestration benefit too. So where do you find all this information? So everything I've run through is based on data. I've used averages, either the average from a group of EPDs or a result of a generic LCA study of the material. Using an average at the beginning of your building design, before you know who the specific supplier will be, can give you an indication of what your final result is likely to be. But data varies hugely across manufacturers, across regions, and across time. So there are a few things you need to keep in mind. The best source of data of a building material or a product is the EPD, the environmental product display. And this is what we would like to see building designers and specifiers demanding from their material suppliers. We want to see these becoming a real differentiator in the decision-making process. And the most accurate information you'll get is from an EPD that covers a specific product from a specific plant. So use that once you know that that product and that product alone is definitely being used in your project. Failing that, there are EPDs that cover groups of products, either all from one manufacturer using a similar process, or trade bodies that produce EPDs to cover the products of all their members. But there's less certainty here. As you zoom out from a specific plant, then you lose accuracy. And the other thing is time as well. How old is your EPD? An EPD has a valid lifetime of 5 years. After that, it's deemed to no longer fully reflect what's going on in the production process. So you can look for EPDs in a number of places. You can see websites there, and we're working to digitize all this data so that we can create tools to help people create models like this at early design stages. For now, I would recommend that you take a look at EPD Ireland, run by IGBC and the Eco Platform database of EPDs. And if you're a manufacturer in Ireland, there is support to develop EPDs from Enterprise Ireland. And finally, to get you started in embodied carbon, I'd recommend you go to the Circular Ecology website and download the ICE database for free. It's a very, very useful Excel spreadsheet that gives you all these averages I've been talking about. And it also gives you lots of links and background info on all of the materials. And it's just a really handy spreadsheet to have on your desktop for cross-referring, and is often a good starting point for any research that you want to do. And it's free. And finally, when's the best time? So as early as possible before any decisions get made is the best time to start thinking about this. This chart relates to cost, but exactly the same principle applies when thinking of carbon savings. The earlier you set your design direction and get everybody involved and get buy-in, the better, the greater potential for reducing carbon. Trying to shoehorn it in later will be met with a lot of resistance and more costs. So yeah, hopefully that's given you something to think about to start looking into. And finally, if you don't want to look at spreadsheets, I would recommend that you take a look at this website where you can start to look at what's important and what the alternatives are. I think that's it from me. So I'd like to just hand back and I'll stop sharing.
That's great. Thank you very much, Stephen. I'd move straight on. I know there was some questions there posted in the chat box. We'll get to them in the Q&A. Please feel free to respond as part of the participation as well. If there's someone else is posting some very interesting links to other lifecycle assessment databases as well. So that's fantastic. So straight away, I'll hand over to David. So over to you, David.
I'll introduce myself. My name's David Stockdale. Good afternoon, everybody, ladies and gentlemen. I'm a fellow of the Chartered Institute of Building, a Chartered Environmentalist and an advisor to the CIOB Policy Board on Sustainable Development. I also have an interest in the United Nations Sustainable Development Goals, and I am a director of Briga Consulting, which is a CIOB Chartered Building Consultancy. I want to step back before we get into any conceptual detail and consider where the systems, processes and measurements that we are going to see fit into the bigger picture. The world will heat by more than 1.5 degrees Celsius unless nations produce tougher policies. A global stocktake by the United Nations has confirmed this. Governments must halve emissions by 2030 if they intend the Earth to stay within the 1.5 degree safe zone considered by the Paris Agreement on climate change. However, the latest set of national policies submitted to the UN shows emissions will be merely be stabilised by 2030. Putting this into the built environment context, keywords will appear in all the presentations, I've no doubt. Life cycle assessment, a technique to assess environmental impacts at all stages of the product's life, including raw material extraction, materials processing to dispose and recycling. Whole life carbon, emissions resulting from construction and the use of an asset over its entire life, again including demolition and disposal. The interesting thing is a transition to a circular economy, and that is an industrial economy that promotes resource efficiency by replacing a linear take, make and dispose model of production. Next slide, please. The main purpose of life cycle analysis is to identify where improvements can be made to reduce the environmental impacts of a product or process in terms of energy and raw materials used and wastes produced. Next slide, please. I thought I'd take the opportunity I was intrigued to look at the dictionary definition of thinking, and there it is. And there's a lot for us to think about during the process of design and operational. Next slide, please. The next two slides establish that there is a wealth of international briefing documents, statistics, and reports that communicate the issues involved in thinking about the required changes from business as usual. These are various research statistics that I have looked at researching for this presentation. The Ellen MacArthur Foundation was launched in 2010 with the aim of accelerating the transition to the circular economy. Next slide, please. Again, you've got the World Green Building Council estimates, you've got various think tanks, and again, there's an excellent report which is in the list of my recommended reading at the end of the presentation from the Ellen MacArthur Foundation on the circular economy. Next slide, please. Concepts that we've got to consider in this process are listed, but top of the list is systems thinking. That's extremely important that we actually consider the design process as part of a system, an integral part of the whole system that actually is tackling climate change in terms of adaptation and mitigation and delivery of buildings and assets that actually will contribute to actually changing the status quo and moving on to a decarbonised path at net zero. Next slide, please. This slide split into linear economy and circular economy. So just going through the linear economy, you've got basically a post-industrial, actually was born in the Industrial Revolution, if you think about it, and now we're suffering from its legacy. The costs of pollution were not incorporated into global economies and were subsequently ignored. We need to move to a circular economy. The technologies we use every day might change, but our primary need for energy will not. If you look at the two red boxes, starting with the rare materials that input into the energy and material input box. The more sustainable world is largely dependent on rock-borne substances called rare metals. According to Bruin Petron in his book, which I've referenced at the end as one of my recommended reading lists, The Rare Metals War, the potential demand for rare metals is exponential. We are already consuming over 2 billion tons of metals every day, the equivalent of more than 500 Eiffel Towers per day. We will increasingly rely on the rare metals that are driving the impending transition to a decarbonised economy. Just give you some examples there. 8.5 tons of rock need to be purified to produce 1 kilo of vanadium. 16 tons for a kilo, 1 kilo of cerium, 50 tons of rock for the equivalent in gallium, and 1,200 tons for 1 kilogram of the rarest of rare metals, lithium. Now, what does that mean? Who cares? Rare metals are found in minute proportions in more abundant metals, making their extraction and refinement expensive and difficult. There are about 30 or so rare metals. Mining these metals is anything but clean. There's a dark side to digital and communication technologies that the construction industry depends on. Existing technologies such as wind turbines, solar panels and electric cars are packed with rare metals to produce decarbonised energy. Even technologies based on combustion engines use rare metals to make vehicle and aircraft design lighter, more efficient, and therefore less fossil fuel intensive. Rare metals are used in a variety of ways across industry. For example, making magnets to power electric vehicles. The transformation to a decarbonised economy will be driven by digitalisation powered by electricity, which in turn will rely on the extraction and processing of rare materials. Next slide, please. This slide introduces common activities within a product's or asset lifecycle boundary. Lifecycle studies require careful attention in setting boundaries between the construction system under study and the environment, so that the interpretation of the data generated is fit for purpose. System boundaries are a set of criteria that defines which processes are included within the boundaries of assessment. And then there's nothing there which should shock anybody in terms of a life cycle boundary where it encompasses raw materials, manufacture, distribution, retail, consumer use, and disposal and recycling. When I referred to the use in the previous slide in terms of consumer use, that is an important aspect which we'll get onto later in the conclusions, that we've got to change the way we consume. Because if we don't change the use within the economic model of the closed loop system, we're not going to achieve much in terms of meeting any targets. It's the human element of what can be a design problem, but design is an integral part of a larger system. Next slide, please. What I mean by that is that, according to Aristotle, and I've got no reason to doubt him, the whole is greater than the sum of its parts. Life cycle and whole life carbon thinking is part of a larger system that will help us understand both embodied and operational carbon within the built environment system, which is a subsystem of achieving the net zero carbon targets, whichever country you live in. The UK Committee on Climate Change's sixth carbon budget includes industry sector pathways to net zero for the manufacturing and construction sector, which is a system within itself. Next slide, please. So there's a definition by Peter Senge of what a system is perceived to be, which is nothing that is mind-shattering in terms of inputs, the system, and the outputs of the system. But what is important is the system boundary, because if any part of the system contained within the boundaries is changed, all the other inputs and outputs will also change. Next slide, please. What do I mean by that? So this slide is a generic slide that typically lists the activities and identifies activities within a product asset lifecycle boundary and the impacts of the system. Data and digitalization has a key role in terms of product inventories of environmental impacts and information management using building information modeling. Inventory analysis involves the collection of data about the products or services being investigated and the quantification of relevant material and energy inputs and outputs. Impact assessment generally involves evaluating data collected on the material and energy inputs in terms of their potential environmental impact. The interpretation of data combines the findings from the inventory analysis and impact assessments to allow conclusions to be drawn and recommendations to be made. Next slide, please. Here's an example from the water industry. Embodied carbon is sometimes referred to as capital carbon, referring to the emissions associated with the creation of an asset. In terms of buildings, the embodied carbon used to create a building may be as high as 62% of its total whole life emissions for some building types. As was mentioned previously, the relative significance of embodied carbon is increasing as both the grid decarbonizes and operational emissions decrease due to increased efficiency, according to the UK Green Building Council. Next slide, please. The CIOB has published the Code of Practice for Project Management for Construction and Development. Within that document, and it's an excellent document of best practice, briefing notes 2.01 on sustainability issues recommends key actions, and those key actions involve life cycle impacts on materials and equipment must be considered by the project team, as well as the selection of construction methods. Another key action is to make the project team aware of the principles of designing for deconstruction and consider the whole life of services components for recycle or reuse at the end of their life. Now, this is part of a series of briefing notes, best practice checklists, that is designed to make sure that all elements of sustainability in terms of project management are considered by the project team. So this is now being embedded within best practice formally rather than via CPD and training courses. This document should be the Bible for a project manager in construction and development. Next slide, please. Right, these are examples of best practice resources and tools that is generally out there. The Building Services Research and Information Association have excellent documents on lifecycle assessment. Embodied Carbon is the Inventory of Carbon and Energy, the ICE. There's the guide, PSI guide, PAS 2050, in terms of assessing the life cycle of greenhouse gas emissions for goods and services, a very good document. The Green Guide to Specification by the BRE, ISO standards, and PAS 2080 is the specification for managing whole life carbon in infrastructure. The list is not exhaustive, and there are common elements of these resources, tools and techniques that apply across the board. Next slide, please. These are required tools and outcomes that bring the thinking process into reality. Work/product breakdown maps, process maps, and reporting are crucial in terms of the exercises that have to be done. Again, there are lots of tools and lots of techniques. I've just chosen those three because those are the three that are fundamental in terms of the process as a whole. Next slide, please. There are many databases and services listed on the internet. The process is well established. These are some example tools that you can find on the internet. It includes BRE, databases, and various other national and international databases in terms of what supporting tools you can actually discover and use on embodied energy and carbon, environmental impact indicators, etc. The BRE Impact Database for construction products has probably 350 data sets that are compliant with the British, which is compliant with the EN standard 15804. So it's out there. There's tools out there. You know, not really the question of the tools. It's the thinking behind the tools, and that thinking behind the tools actually is a small component on a system and subsystems to achieve the objectives of impacting on climate change. Next slide, please. So what do we do make of the thinking behind life cycle and whole life carbon? What does it mean? The key drivers moving forward must be keeping up with innovation, digitalization and communication, systems thinking. Personally, we have to keep abreast of the situation and developments through continuous professional development and behavioural change. We're talking about people here, and there's a danger of getting too technical and talking about the mathematics of design and designing embodied carbon and considering operational carbon. But we are talking about people and their behaviours. You know, what's changed in general behaviour, what's changed in business as usual. And basically, a really big impact that is not usually considered is the consumers of the results of various exercises on life cycle and whole life carbon. Digitalization and communication will dominate the future, in my opinion, powered by electricity, via information management technologies that include the use of building information management. Digitalization and communications technologies will rely on rare metals extraction, which in turn rely on supply to meet exponential demand in the future for rare metals. Supply and demand has got to be matched and considered before we agree on any methodologies and strategies, because you could be taking more out of the environment and the earth than we actually think we're going to do. The potential for product standards to address industrial emissions is another key driver to achieve what we need to achieve in design. We need to clearly understand future thinking about life cycle and whole life carbon to meet the challenges of a decarbonised future. Earlier in this presentation, I offered a definition of thinking. One of the dictionary definitions of thought is careful and considered and attention. There is a purpose to this type of thinking. It's not an isolated technical process. Change the way we produce and therefore consume goods, services, raw materials, and energy is our next great challenge. It's a people challenge. Digitalization and the energy transition are codependent. Digital technology advances and enhances the impacts of green technology. Rare metals have become indispensable to new information and communication technologies for their semiconducting properties that regulate the flow of electricity in digital devices. The UK Climate Change Committee 6th carbon budget sees electricity as a major driver in achieving the UK's net zero carbon target. Any plan for decarbonisation should consider the environment as a whole system for water, biodiversity, health and well-being, all within a consumption context. This will be facilitated and delivered through excellent design, supported by life cycle and whole life carbon thinking, and the transfer of lessons learned and best practice. Next slide, please. Here's a list of recommended reading. They're all a damn good read, but it gives you an opportunity just to have a think on a wider context and consider what we've got to do. Nothing's certain at the moment. Strategies are still being developed, whichever country that you live in. We're not all together. We're not all singing from the same hymn sheet, not yet. And it'll take a great challenge to do that, especially with COVID-19 pandemic. We punch out something like 51 billion tons of carbon dioxide equivalent per year annually. It's worth thinking about in terms of what we can do within a small context of a larger system to influence how we go to deliver what we need to deliver and meet the challenges that face us. Thank you very much.
Thanks very much, David. That was excellent, highlighting the importance of systems thinking that we need in the transition to a circular economy. and a nice suite there of references and resources for people to get started with. So I'll go straight on to Mirko, if you're ready, Mirko. Yeah, over to you.
So I will share my screen. Just a second. Okay. Can you see my screen?
Yeah, all good.
Okay.
Oh, you're in presenter mode, I think. There you go.
Yes, yes. Right, okay. So thank you. And well, hello, everybody. So my name is Mirko Furnitani. I am the Embodied Carbon and Circular Economy lead at Hilson, Moran. We are based in London, but we have a few offices in the UK as well, in Manchester and in Cambridge. So our company, it is an international environmental engineering consultancy company, and we provide a lot of different kind of services. And of course, we provide sustainability services as well, and we basically, we are active in a few different kind of sectors, for example, commercial, fit out, education, and etc. Okay, so just to introduce the subject, which is the whole life carbon, I'd like to introduce the subject by showing this slide, which is an extract from the LETI Embodied Carbon Primer. I don't know if you are familiar with LETI, but LETI is the London Energy Transformation Initiative, which is a group of voluntary people from the industry, well, basically, this is the work we did in 2019, and I was at the time the Embodied Carbon Primer lead, and we prepare a couple of publications which are available online to be downloaded for free. So I would suggest to go on the LETI webpage if you would like to download all of this information. But anyway, just to talk about the whole life carbon and of course the importance of circular economy with it, is that when we prepare this for LETI, we basically thought that what is very important in order to address all life carbon, and particularly all life net zero carbon, is the importance of integrating circular economy principle within the design. Of course, because the concept of life carbon, it is obviously the operational carbon plus the embodied carbon. And of course, the importance of integrating circular economy, of course, will affect the embodied carbon impacts. We produce a kind of roadmap for achieving net zero carbon in the future, well, presumably in 2050. And what we basically recommended was that every building, let's say from now on, should be built by using, for example, reused material, and of course a big part of the building elements should be reusable at the end of life, so that at the end of life of a building, it would be possible to have a group of building elements which are going to be possible to be used in next lives. So this is of course, we are in this kind of transition period at the moment, and because we are basically now in a kind of system called the linear economy, and we are gradually shifting to what is called the circular economy. And of course, this is a more in-depth visual for explaining the concept. Before David and Stephen has anticipated something, but so in other words, what you can see from here is that, of course, to the top is the linear economy, which is typical, like, taking the resources from the nature, use all the resources for production of products, use and then waste everything. The circular economy concept obviously takes into consideration the fact that obviously the resource extraction should basically be minimized, and of course at the end of life waste should be minimized as well. And what it is possible to be done to achieve those two aspects, it is to basically keep as much as possible products and building parts within the loop. Particularly, all of these action, it would be possible to be done by going for a few strategy. And all of these strategy are, for example, in terms of building element system and etc. Of course, it would be possible to do, for example, maintaining and repairing building parts, perhaps reusing building parts, within the building throughout the life of the building. Of course, it is a good idea to go for remanufacturing of building elements. And of course, recycling, it is another very good aspect for it. Now, if you can see the way, all of the actions are put on into this slide, it is very interesting that obviously recycling, it is perhaps what it should be taken as a last resort, because of course recycling means to basically go for a dismantling, perhaps demolition as well, and of course going for additional processes for processing waste at the end of life, and of course send everything to the recycling facility. Now, if you consider all of these processes, obviously they are energy and of course carbon emission processes, and of course the goal for achieving net all life carbon obviously is to minimize carbon emissions as well. I think two important aspects for it is that in order to contribute with the circular economy concept, what it is very good to be done is to move, let's say, from buying product to basically leasing, and to go for servitizations of products and system. Of course, it is because they contribute a lot in, of course, reducing, the environmental impact of building materials, and of course they contribute into, circular economy aspects as well. If you would like to read more about, all of this concept, you can double check the LETI Embodied Carbon primer, which is, as I said, available online. Going to the next slide. So I'd like to introduce this project because it was a very interesting project where I was involved when I was at BRE between 2017 and 2019. Well, basically, I was mainly involved in this research project, which was founded by the European Union. And so I was basically the life cycle assessment lead for the environmental evaluation module of this project, which is called Building as Material Banks, or BAM 2020. You can basically, what we did in this project was that the main goal was to basically enable circular economy into the construction industry. And what we basically did was we tried to integrate into only one platform, any kind of environmental evaluation in terms of assessing products and building, any kind of economic evaluation in terms of, well, coming from building a building. We work on a module called Reversible Building Design, which is basically how to design a building in order to be able to be demounted at the end of life. And of course, the integration was with a digital platform, which should be based on a BIM language as well. I mean, all the research project was based upon building a material passport as well, because of course it is an important part of information, how to gather information and how to transfer information from throughout multiple life cycle of buildings. And of course, the outcome of it was going to be a multiple key performance indicators. Now, all the material is available online, and I would strongly suggest you to go on the website in order to see everything which is available, because it was produced a lot of documents, and of course it is always good to read about perhaps what it has been done in a research projects. There are a lot of documents to be downloaded, so it could be very useful for you. In the meantime, I was working on this project. There were a few pilot projects that were going to be developed, and particularly one of the pilot projects was this particular building, which is called the Briga. And this particular building was basically designed to be fully demountable at the end of life. And of course, the main goal was that it would be possible to reuse the majority of the part of the building for building another building at the end of life. Now, the main goal of this research project, particularly for this pilot project, was that the building was be able to be built, for example, as the configuration of brick 1, then to be demounted at the end of life, and then of course to use all the parts coming from the brick 1 to build the brick 2. And of course, at the end of life of this building here, what it was possible to be done was that could be possible to be demounted again and rebuild the configuration of brick 1 at the end. Now, if you can see on the right-hand side, this is the embodied carbon assessment. It was carried out by, for assessing this project particularly. And we were particularly interested in to see the embodied carbon impact in going through, for example, what is called, let's say, a business as usual route compared to a circular economy route. Now, if you can see, well, those two approaches are highlighted in this graph here. And, you know, the orange line basically shows the embodied carbon impact of a business as usual building. So in other words, by building those three buildings, considering that we need to procure material for building and demolishing at the end, and to do so for brick 2 and again for brick 1, this is basically the embodied carbon impact was calculated. If, for example, all of these processes, instead of to go through the business as usual route, it would be possible to go for a design for disassembly strategy. Of course, what the project achieved was this impact shown on the green line here. Now, of course, you can see that it was possible to save, obviously, carbon. And this, of course, comes from the fact that I mean, a lot of materials and the system and products obviously were not disposed at the end of life. And of course, what it happened was that reused material basically do not generate any emission in this case. And of course, you know, the savings is obviously evident. Well, of course, another important aspect is not only the carbon saving at the end of life, but what is very important here is that you know, there was no procurement of new materials, so that obviously we can preserve natural resources as well. So the results of this project here, particularly what you see in this slide here, is available online in this publication. I was the co-author of this publication, so it is freely available to be downloaded. So, you know, feel free to download and to check more detail on yeah, this publication. Okay, next slide. So this is, let's say, a real project where I've been involved at Hilson Moran, and well, basically the concept is more or less the concept. It was basically analyzed in this research project, but in this case, obviously, it is applied to a real case studies, let's say so. So in this case, we basically were appointed by a client that basically they would like to have they would like to apply, you know, cradle-to-cradle principle to for developing new buildings in their portfolio. Now, well, this client was basically very keen on in achieving, you know, the UN goals, and particularly a few categories here. Well, one of them obviously is the 13, which is the climate action. Now, because of this obviously commitment, well, the client wanted to have wanted to basically maximize the environmental benefit in building something. And of course, a good route to be explored was to go for designing for the cradle-to-cradle. Now, what we did in this particular project was that we produced a cradle-to-cradle development guide. And of course, this development guide obviously should be the base for building, future buildings which are going to be built by our client. Now, the principle for doing so, what we did was that we were asked to basically take an existing building, which is this one, and we were asked to basically redesign this building here into what it is called, let's say, a cradle-to-cradle buildings. And so basically what we did was that we basically got involved with the design team, and of course the first action we went through was obviously to find out the way to build a building using a lot of low carbon measures for both, obviously, for reducing embodied carbon and operational carbon. So we went through a pretty comprehensive analysis of a lot of material to be used, a lot of low carbon material to be used for building the building. And of course, we went through a pretty big exercise in order to understand how the building could be demounted at the end of life, and particularly how it could be possible to be demounted building elements without compromising their reutilization in the next life. I mean, of course, what we did was that, part of our brief was that the building had to be last for 25 years. And what we assumed was that this building here could be basically built in a location and at the end of life to be demounted instead of demolished, and of course that it could be possible to be relocated 1 kilometer far away from the original location. Of course, this is obviously, we prepare a development guide. So in other words, this particular action, it could be done by obviously moving everything more far away as well. So it could be rebuilt even 200 kilometers far away. It's not a problem. Of course, in that case, what should be taken into consideration is the transportation emissions as well. But anyway, let's say throughout, this exercise, and by applying all the reversible building design and the possibility of demounting a building at the end of life and to be rebuilt in a next life, it could be possible to basically achieve this kind of results here. Now, if you consider that there could be a 56% carbon reduction, going from this particular building to this one, of course, from my point of view, it is a pretty big achievement, obviously. Now, I think what it would be very interesting to see is how much would be the all life carbon in, for example, building the next building after the building number 2. Of course, I'm expecting that a lot of embodied carbon emission will be definitely even more intensive, because a lot of building elements will be sourced from, the building 2, obviously. Now, what I can say going for this project, what I can see is that, of course, it is it is visible that it was possible to achieve a very low carbon results. But I think what it is important as well is that there will be an economic benefit as well, because of course, if well, let's say if this building here is built by a owner and occupier, obviously, well, of course, it will cost. Well, the capital cost will be high at the beginning. But of course, you know, in building the second building, obviously, the capital cost will decrease drastically because, of course, a big part of the building elements will not be needed to be sourced. So, in other words, you know, I mean, together to, you know, embodied carbon saving, there will be capital cost saving as well. And I think this is very important as well for obviously a developer. And that's it. Thanks very much.
Thanks very much, Mirko. Excellent. And putting a few links in the chat box there, referring to the BAM project, which we love. There's so much resources there. A fantastic project. So I'd just like to hand over finally to Dermot. I know some of you are posting questions, so I'm going to collate them for the Q&A at the end. So over to you, Dermot.
Okay, how are you doing? Sorry, I was trying to unmute myself, but I don't think I could. Thanks for having me. My name is Dermot Kehily. I'm a lecturer in TU Dublin. I have an interest in sustainability, life cycle costing, and embodied carbon life cycle analysis. And I've done some research in the past. My PhD was related to sustainability and building information modeling. So just going to come in on the coattails of the previous two speakers, excellent presentations. And I'm going to talk about how we calculate carbon. I'm a quantity surveyor, member of the Society of Chartered Surveyors. So I'm going to come at it from a quantity surveyor's background and use some of the methodologies that are proposed by the Royal Institute of Chartered Surveyors. So just share my video. How do I do that? On share, the share screen. Yeah, there we go. And okay, just clicked it. So life cycle costing and life cycle analysis, the reason I'm kind of putting them two up there at the same time is they kind of essentially, from a QS's perspective, one is an economic evaluation of sustainability, and the other is obviously a calculation of embodied carbon, a metrics of also of measurement of sustainability. A lot of the assumptions we make as quantity surveyors, evaluating cost and whole life cycle cost on a building, is similar in both evaluations. When things get replaced, what kind of maintenance profile we have, what's our operational cost, and thus, what's our operational needs in terms of energy, and thus obviously that has an effect then in the production of carbon. So we're kind of well placed, quantity surveyors, given the fact that we have a background in quantification and calculation of our building materials, to, instead of using, I suppose, rates in terms of cost, use a calculation of carbon in terms of calculating the embodied carbon of the building. What I'm going to refer you to today is obviously the international standard that governs embodied carbon calculations is ISO 15978. But the RICS have published some good documents in relation to calculating embodied carbon. One in 2011, I believe, methodology for the calculation of embodied carbon of materials, and then one a couple of years ago, which was kind of building on that as a second, even though it's it was the first, it was noted, it was the first edition, essentially built on the original methodology that's on the top there. And that one is the whole life carbon assessment of the built environment. So basically these are kind of information papers that interpret and propose a methodology on 15978. And they're a good kind of start for, let's say, construction professionals calculating embodied carbon based on quantification of their building materials, be it if they're QSs or engineers or even contractors trying to give their clients an idea of maybe one option versus another option in terms of the embodied carbon content of their particular project. I'll refer you back quickly to the stages of life cycle assessment, from your cradle to gate kind of analysis, A1 through A3, through the construction stage, the use stage, and the end of life stage. And then obviously D is the circular economy, and possibly using some of that recycled content back in the earlier stages of the life cycle analysis. So that is what we're essentially concerned with from a kind of, I suppose, a construction and operation point of view in relation to our kind of life cycle analysis. Looking at embodied carbon, well, why is it becoming important? Well, as we kind of sort out, and I'm not saying that we have sorted out, certainly not in our existing construction or building stock, but from a new build point of view, as we kind of sort out and move towards more of a zero carbon operational point of view, our embodied carbon on our new builds are becoming more and more important. So yeah, we could get zero carbon from an operational point of view, but if we're using a lot of steel, if we're using a lot of concrete, the embodied carbon in our buildings could be, quite excessive. So embodied carbon is becoming more and more important, because what was the majority of our carbon produced through the operational phase now is getting dealt with. Our embodied carbon in terms of kind of, I suppose, the manufacture and construction and use during construction of those building materials are becoming more and more important. Just a kind of quick, just to give you an idea what the embodied carbon at the moment, well, this is a 2017, so a couple of years ago, a 2017 analysis of an office building versus a warehouse versus a kind of residential construction over, I believe it could be a 60-year period. I think it is a 60-year period in terms of kind of a life cycle analysis. The embodied carbon of your office building, again, about 60% of the overall carbon content, which includes the whole life, the operational carbon as well. Warehouse is a good bit more, and that is probably to do with the building materials used in that warehouse, be it steel construction, concrete construction, and your residential is up there about 70%. So between 60 and 80%, between 60 and 70, 80%, our embodied carbon now with new builds is pretty much the focus, and should be the focus in relation to what we're looking at as we get sorted in relation to the operational carbon. So as quantities surveyors or as construction professionals looking to give our clients an idea of maybe one building versus another in terms of one more sustainable option versus something that's more traditional, are using building materials that are tread lightly on the environment, so to speak. What kind of methodology should we use? Well, the RICS, the Royal Institute of Chartered Surveyors, and I'm using their methodology probably in lieu of something that possibly is not completely related to our profession or my profession, and using their direction. They're saying to kind of use the breakdown structure that we use as quantity surveyors in our elemental breakdown, which is quite useful because that's the way we put our cost plans together. That's the way we put our bills of quantities together. So if we have that information and we have that quantification, well, then what we're trying to do is essentially use a kind of a embodied carbon unit rate as such, rather than a monetary unit rate. So we have the methodology already. We've been doing it forever. And it's just a matter of kind of changing that practice a little bit for carbon counting. So this is, bill of quantities, and might be a little bit blurry, so apologies for that. But essentially it's a breakdown, a good detailed breakdown structure. And the units there on the left-hand side are assigned a quantity, and then obviously they're assigned a rate, and that rate times the quantity gives us our cost. So if we can imagine, if we use a kilogram per CO2 emission per unit, multiplied by its quantity, will give us, I suppose, that unit cost for each particular item. So as quantities of errors, if we take it on a kind of an item by item basis, we can pretty easily, because we've already got our bills of quantities, we've already got our cost plan, we can pretty easily and quickly build up, I suppose, a BOQ, bill of quantities for embodied carbon. This kind of just outlines digitization and where we might go and how we might leverage it. Again, a bit of a pet interest of mine from a digitization point of view, or your building information model. There is plugins to the likes of Revit that you can use that have databases attached to them. So certain software like LCA one-click, and basically that software gives us the opportunity to assign embodied carbon content to our object properties of the model. So it makes it a whole lot easier using these models to quickly assign, I suppose, carbon content to the objects in the model and then run a simulation that outputs the carbon content. Before that, we would have had to quantify per kind of a 2D takeoff, assign, I suppose, generate a quantification, assign a unit rate per that unit, like I just showed you in the last slide, and build up our embodied carbon cost plan like that. But I suppose with building information modeling and with digitization, this whole process becomes a lot easier to calculate the LCA on a particular project. So where do we get the information? And it's been mentioned before, well, from a QS point of view, we can get it from generic databases like what was mentioned before, the ICE, the RICS, in conjunction with RAP and the United Kingdom Green Building Council also have a database. Briga is a database in the UK too. And of course, we can get the actual specific information if we can attain it in relation to the EPDs. So in Ireland, we have an EPD platform from the Irish Green Building Council, and it's just getting started. I believe there is a certain amount, I don't know how many, 50 or so, maybe more now, EPDs from certain manufacturers, certain suppliers on there, and hopefully that will grow over time. So the more EPDs we have, the more data we can get and apply to our embodied carbon calculations. So that's a useful repository. What do they look like? Well, there's a number of different metrics in relation to an EPD. This one here is for paving block, 80 mil silver granite. It's the first one there, the global warming potential, basically the embodied carbon that we're interested in. So on the top, you'll have basically the life stages, or the stages of the life cycle analysis of that particular product. Now they can only really provide A1 through A3, and that would be the actual manufacture of that material and that transportation off site. So the cradle to gate analysis. The cradle to grave analysis then will have to be calculated by the actual, I suppose, the user of this EPD in relation to trying to figure out how, what the transportation length is from the gate of the factory through the site, or from the warehouse to the site, and then the actual construction of that material and the use of certain, I suppose, plant machinery, etc., in the production and construction of that material. And in that case, then I suppose you're calculating A4 through B and through C to try and get your kind of whole life cycle analysis of that particular product. Most embodied carbon calculations I've seen, at least in the recent past, have been done cradle to gate. We're only kind of really getting our heads around how to calculate cradle to grave, and then even further in terms of the circular economy. But I think that's something we'll be moving into, quite easily, hopefully, within the next couple of years. So calculating, I know I'm out of time really, but I'll run through these last couple of slides quite quickly. Calculating embodied carbon based on the RICS methodology, both the 2012 version and the 2017 version, can be done quite easily, as I said before, because we've got the bill of quantities. Essentially what we're looking at is the units. We're looking at the elements, which would be maybe a cavity wall construction. We're looking at the outer leaf, the inner leaf, and we're assigning it basically an embodied carbon calculation to each unit in that particular element, so to speak, including our insulation and our wall ties. We're adding them together and we're coming up with basically a kilogram per CO2 per meter squared or meter cubed, depending on the building material. As I said before, most of our analysis are really from the A1 through A3 stages, that cradle to gate, but again, we're being pushed into the realms of cradle to grave now, because that's really the meaningful calculation that we have to kind of come up with in relation to what the embodied carbon content is through the whole life cycle analysis stages, not just your cradle to gate. This is an extract from a student of mine who did a fantastic thesis last year, Aoife Morris from Kerrigan, Shane and Newman. And she basically took a bill of quantities and instead of assigning, I suppose, your cost per unit, she assigned an embodied carbon kilogram per CO2 emission unit to each particular item in the BOQ. And she was able to kind of look at the benefits and challenges in relation to that. And, you know, the real, I suppose, benefit is we have the BOQ and it's getting access to the data, and more we have that data, be it through EPDs or be it through generic databases like the ICE. So it's not as challenging for quantity surveyors or for anyone doing these things if they can get their hand on a BOQ or if they can get their hand on a cost plan in terms of quantification. It's a matter of kind of assigning, I suppose, unit rates to that. And there is very good software out there that can help in this regard, like the one-click system that the Irish Green Building Council utilises. That's a fantastic system in relation to doing, you know, quantification and utilising models and coming up with an embodied carbon calculation on a particular building, on a particular project. Just a couple of things. Not all, possibly not all the elements of the building need to be focused on. I mentioned before that, you know, a lot of building materials, and it has been mentioned before, are carbon hotspots. So your foundations, because they're concrete, your external walls and internal walls, because they're blockwork or they're concrete, your frame, because they're steel or they're concrete, your windows, because they're possibly aluminium or PVC. These are the, I suppose, the carbon hotspots of a building. And you can see from your regular 3-bed semi-detached house in Ireland here that between your poured concrete, your concrete elements, your steel, you've got, again, you know, 50, 60, 70% of the embodied carbon of that particular building. So to start with, if you focused on maybe the substructure, the superstructure, and even possibly some of the, you know, some of the mechanical, be it the ductwork, etc., and some of the finishes, you know, the kind of 80-20 rule of quantity surveying, 20% of the quantities will give you 80% of the cost. Well, same could apply to your carbon counting. So 20% of the quantities is essentially 80% of the carbon, and that would kind of ring true with this statistic. So from a QS point of view, or from a carbon counting point of view on a project and measuring sustainability, those are the materials to focus on, and the methodologies allow for that, rather than looking at every little tiny little bit that could take an awful lot of time but doesn't really add a whole lot of value. Some buildings, and focus on buildings, well, this is an extract from the methodologies from the RICS, and you can't really see it there, but it's your high-rise construction that really has large bearing in relation to the embodied carbon content of those particular buildings, because they've got the steel and the concrete and the frames that have to go with it, and obviously the elaborate mechanical systems that need to be kind of accommodated in buildings like that. So they're above average. Also, buildings like sports facilities and hospitals are above average in terms of their embodied carbon content. So again, it's possibly even more important to focus on embodied carbon in those particular buildings than it may be in, you know, house construction that are quite average in terms of the average data that comes out of those particular type of buildings in terms of embodied carbon. So that's my presentation. Delighted to be part of this series, and if anyone has any questions on that, and I can share any part of that presentation with you. By all means, give me an email, dermot.kehily@tudublin.ie. Thank you very much.
Hey, thanks a million, Dermot. Actually, Dermot, before you mute yourself there, I just put we go retrospectively back to the questions. A question that was just posted there while you were speaking was the use of bit of quantity type information to calculate embodied carbon suggests that the design is already complete, but it would be instructive to do it at a much earlier stage. How would you undertake such an assessment at a very early design stage when the key decisions are required to be made?
Yeah, that's a good point. So you could do it just like you do your cost planning from a kind of, I suppose, giving your client an idea of cost at different stages of the design and beyond. The same would go, and possibly more important from an embodied carbon point of view, because there was a slide on there and I took it out because I knew I had less time than I anticipated. And it's just like cost. So your real ability to affect the cost of a building is as early as possible. So as at the early stages of concept design. The same goes with embodied carbon. So it's those decisions at the early stages that has the greatest bearing in relation to embodied carbon. So it's at that stage you'd have to leverage whatever documentation you have, be it its conceptual drawings, early mass models, building information models, quantify it as best you can. And it may be, instead of using EPDs, which are detailed specification from certain materials, you're using generic databases to come up with your, I suppose, your carbon counting. So yeah, very good point. It might be moot at that stage that you're kind of calculating embodied carbon on a BOQ in that detail. But I suppose what I was really trying to get across is we have the skills in terms of quantification, be it no matter what stage it's at. And it's a matter of applying your embodied carbon calculations to those quantifications at that particular stage, be it early or later, depending on what the client needs and wants.
I suppose Deirdre makes an interesting point about your 80-20, 20-80 split rule. Maybe that as a sort of pre-development decision guidance, a rule of thumb, if you like, to try and get people to think about it at that very early stage. It was just a nice way of putting it. So I'll just go on to a question for Stephen, I think. If the host can unmute him there, I think that he's muted. I see him looking at me worryingly and a small caption up. And maybe I'll go to Mirko, who's not muted. Mirko, just a couple of questions there. One about the reversible building and deconstruction and demountable construction. How is that conducive with the whole issue around air tightness in buildings and the move towards passive construction and so on?
Yes. Okay. So, well, perhaps the air tightness normally in a building, it is provided by either a membrane or through could be, let's say, OSB layer as well. Now, well, of course, there are other solutions as well, but those two are perhaps the main two building, products you can use. Now, what it is important to understand from reversible building design theory is that unfortunately it will not be possible to demount 100% of your building and to reuse 100% of your building in the next life cycle. Unfortunately, there will be a few building parts or building elements or material which, of course, will not be possible to be demounted at the end of life. And of course, in this case, obviously, you have to procure again in order to provide the same performance as it was before. So, well, perhaps, yes, the air tightness, I believe, is going to be one of the crucial building layer that perhaps will be not possible to be reused in multiple life cycle.
Okay, yeah.
Well, I guess if it's a matter of membrane, perhaps no. Perhaps if the hair tightness layer is made by OSB boards, it could be more possible.
Yeah. And another question, and this is, I suppose, I think I know the answer from an Irish perspective, but just from an EU perspective, it says we often hear that the inhibitor to reuse materials and building elements is the whole quality assurance and verification, whether it's too expensive. Have you had any experience around that?
Well, I understand the problem, and well, what I can say is that the circular economy concept and of course the cradle-to-cradle approach, it is a fairly new approach in the industry. And of course, there is for building products, obviously, is a matter of certifications, warranty, and etc. Now, what I can see is that there are a few institutes which are basically which are established basically recently, that basically they provide certifications of reusable products as well. So in other words, if a reused product it is certified by this kind of institute, obviously will have the same warranty as it was perhaps as new, or perhaps it would be valuable to use in any kind of new building. So now what I can say is that perhaps we are, let's say, at the beginning of the process, and I'm expecting that in the future this kind of certification institute will grow, and of course perhaps regulation will change as well.
Yeah, and I suppose there's probably a direct link with the whole environmental product declaration approach of things as well. And just a final question, Mirko, there, just about the case study that you presented looked really interesting, and
yes,
the Cradle-to-Cradle development guide. For the 50, I think you mentioned the 56% saving in the embodied footprint. What exactly, one of the questions, what exactly gave you that saving? What specific strategies or initiatives within the...
Yes. So in that particular case, the comparison, the 56% reduction, it is the comparison between the existing building and the building number 2, which is going to be deconstructed and rebuilt after, let's say, 25 years in that case.
Okay.
So the 56% reduction, it was, let's say the system boundary of that reduction, it is a all life carbon, so operational and embodied. And of course, the comparison was, of course, operational energy comparison between the existing and the design building. The integration of low carbon products and measures in order to deliver embodied carbon products. And of course, all the operational energy strategy for reducing, operational consumption in the design building as well. And of course, a big part was obviously the fact that a lot of material will be possible to be demounted and remounted again after 25 years.
Yeah, so they hold their embodied value over that longer period of time. I suppose, I think Stephen is stuck on mute. I'll put the question out there that I was going to put to Stephen, but maybe Dermot might be able to come in on this. It's about the whole area, or Mirko or David, that the embodied carbon of timber, how does the end-of-life process affect if it's used for biomass for incineration? And then the question is, how much timber is recycled and reused at the end of life post-incineration, a typical route in Ireland? Just from the construction perspective, a lot of material that's even segregated on site from a timber point of view, if you have segregated timber that goes off for processing and so on, usually the waste management contractors can provide information of where it actually ends up if you ask them for it. But often it would appear on your waste and monthly waste reports as just CD waste. So you have to specifically ask for the segregated materials. But does anybody have any comments on how does it affect the end of life process if timber is going for biomass or for incineration?
I can pick it up this if nobody else. Yeah. Okay. Well, perhaps Stephen could say something, but he's on mute. So I think timber, it is an interesting material because of the quality of the biogenic carbon of the material itself. Now, of course, this obviously, timber is very crucial in terms of end-of-life treatment of timber elements or wood-based products, basically. And of course, it really depends on the kind of end-of-life treatment for timber, because of course there will be different emission associated with it. For example, timber could be used for energy recovery, for energy production with, of course, in that case, there will be benefit because, of course, timber will not be burned only, but, energy will be recovered as well. Of course, it could be recycled in any other kind of wood-based product. It could be, for example, cheap wood. And of course, in that case, perhaps the emission, of course, will be completely different from energy recovery. But I think from my point of view, the best way to treat timber at the end of life is to reuse it, because of course we can minimize, obviously, we can avoid all of these processes for end of life treatment. And of course, I think the most important is that if you reuse a piece of timber, obviously you can preserve the carbon sequestration, and you can transfer from a cycle to another one.
Yeah.
I
think now Stephen is not on mute anymore, so he could add something.
I would just like to, hello. I would just like to add to that. The carbon sequestration, I think, as we see more whole life carbon analysis happening on buildings, and you include the carbon sequestration, there's this temptation to deduct that number from your CO2 per square meter or per whatever it is. Now, that's fine if you have got a plan for your sequestered timber. So if you have a reuse plan, then it's kind of justified. But if you are deducting it at that early design stage, and you don't know what's going to happen in 50 years, as I said in my presentation, if that piece of material is incinerated, then it's as good as if it never actually happened in the first place. So it ties in with what David was saying about how you need to treat your life cycle inventory very, very carefully and set out what's going to happen to your materials at the end of the building's life as well. Otherwise, you will get, particularly when you're pushing for planning permission and you want your numbers to look good, you're going to get people trying to use every trick in the book, including using their sequestration to improve the look of their numbers. So it's all about these system boundaries and how you set them, and the kind of the caveats that you put into your assessments.
Yeah, very good. Thanks, Stephen. We did our best to mute you, but we weren't successful. Look, I'm very conscious of time, so we've run over by 10 or 11 minutes. So I just want to finish up there and to thank Stephen, David, Mirko, and Dermot for all their excellent presentations, and thanks to Suzanne and Shannon for organising the event. And I hope you enjoyed today's webinar, and I hope that you'll join us for the next one on the 8th of April, where we'll be exploring the topic of education for a circular built environment and also announcing some exciting news in relation to a couple of new courses that will be launching as well. So thanks very much, everybody.
Great. Thanks a million, everyone. That was super. Thanks, Mark, as well, for chairing that. You did a great job. There was a huge amount of information and a lot of stuff going on in the chat, which was great. So thanks a million.
Yeah, no panic. See you later.
Take care, everyone. Have a nice afternoon.
Thanks, everyone. Thank you very much.
Bye.